Hi everyone and welcome to my YouTube channel. So we're continuing our review for this year's IMO, which is IMO 2022, which was held in Norway, clearly. And in the previous three videos, basically, we've discussed problem 1, problem 2, and problem 3, which basically were the day 1. Because as we know, day 1 and we have day 1 and day 2. In day 1 we have 3 problems, and in day 2 we have 3 problems as well. So basically, the day 1, we've discussed that. Problem 1 was basically a bit easy, a nice combinatorial problem. Problem 2, if you remember, it was basically a functional inequality, so it was a bit medium, between medium and easy. But the third problem, which was like a number theory, it was really hard. So now we're done with the day 1, and now we're starting with day 2. So basically, in this video, we'll be discussing our first problem in day 2, which is clearly problem 4. So what is exactly problem 4? Well, guess what? We didn't have geometry yet, right, in the IMO this year. So now we are having a geometry problem. So as you can see, like here we're having a lengthy geometry problem. All right, so what are we waiting for? Let's get started. Okay, so let's start by reading like a quickly through the problem statement of this year's problem 4. Okay, so let A, B, C, D, E be a convex pentagon. Okay, all right, so now we have a pentagon already, such that BC equals DE. So we have a pentagon with like a property that the length of BC equals the length of DE. Okay, so not any pentagon. All right, and then we are assuming that a point D is inside our pentagon ABCDE that satisfies 3 properties. So there is a point D inside this pentagon such that TB equals TD, this is number 1, TC equals TE, this is number 2, and number 3 is the angle ABT is the same as angle TEA. So we have 3 properties of this point D. And then like we basically have a bunch of like 4 actual intersections. So basically we're intersecting line AB with CD at P, line AB with CT at Q, and line AE with CD at R, line AE and DT at S. And like we just have some condition that like we have like 4 points on the same order, so like P, B, A, Q occur on their line in that order. The same goes for R, E, A, S, they occur on their line on that order. And then finally we need to show that these 4 intersection points are P, S, Q, R lie on a circle. That means that we need to show that this quadrilateral is cyclic. Alright, so as you see, like we have a lengthy problem, we have lots of points, lots of intersections. Clearly we're going to have like a complex diagram. So not like, for example, just a simple triangle and like some new points. We have already from the first line, we have the first word, like it's basically a convex pentagon, right? Okay, so that like clearly suggests that we're going to draw a very big diagram for this problem, and then like try to, for example, do some angle chasing, do all the stuff we want. So alright, so like the first strategy here is to draw a very big diagram on our paper. However, like one idea that I always suggest is that don't immediately start by drawing a big diagram. Clearly, like drawing a diagram will take lots of your time, like not that much really, but like you don't want to draw a big diagram and waste too much time and then like discover that, for example, a point is outside the paper. So for example, like you need to intersect 2 lines, however, like unintentionally like you draw them to be parallel. Like something like this. So they like you will have to extend them outside the paper, and then like you need to draw the whole diagram again. So like my strategy is simple. Start by drawing a small diagram, and this diagram like you will know basically where all the points will lie. So you will adjust your big diagram accordingly, and this time like you will not waste too much time. All right, so basically like we'll try like to basically just use this a small space here. Clearly like we cannot draw a good diagram here, of course. However, like we just want to know like where all the points basically lie. So like we'll start by drawing a very simple diagram here. So first of all, clearly we need to draw the pentagon here. So keep in mind that BC equals TE, so we'll try to do that immediately here. All right, so we have a simple pentagon. So we'll draw like something like similar to a regular pentagon. So we'll start with the vertex A here, and then something like this, basically AB. Then this is BC, which should be like the same length here, BC, and then CD. Then now this should have the same length as this one. So let's say it's something like this. All right, this one is the same as this length, and then we just connect this back. So this basically is A, B, C, D, and E. And of course, we know that BC equals DE. All right, that's our pentagon. All right, what next? Next, we need to introduce our point T that lies inside here, such that we know that TB equals TD. All right, so TB equals TD. So what does that suggest? What does it mean, like TB equals TD? Clearly, that means that T lies on the perpendicular bisector of basically BD. So like, let's imagine that we've drawn BD, then this, something like this, should be the perpendicular bisector of BD. The same goes for CE, because they are telling us that TC equals TE. So TC equals TE, so like T will lie on the perpendicular bisector of CE. So something like this. Maybe some point right here. All right, this is our point T, and they are telling us that clearly here we have this angled condition. So ABT equals TEA. So we need to draw ABT. So basically this is ABT. This angle is the same as the angle TEA. So TEA. Okay, like don't think that these three are collinear points. This is not necessarily, but here, because our diagram is bad, like here, small, you might think something like that. Okay, so this is basically point T, and this is point T, and we know that this angle is the same as this angle. Furthermore, TB equals TD and TC equals TE. Okay, now we need to do the intersection, the four intersections, and that will really make our diagram really complex, because AB, we need to intersect AB with CD. So somewhere like here, like it will be a bit outside the board. But remember, this is our just first simple diagram, so we may like adjust it as much as we want. So this is point P. All right, so this is point P here. Next, we need to intersect AB with CT. All right, so CT with AB. So clearly, like this will be somewhere here. Oops. So should be somewhere. Somewhere here. All right, so this is our point Q. Okay, what next? Oh, okay, so now we should check that this condition holds. So PBAQ, PBAQ. So indeed, they are already like in that order, PBAQ. Perfect. Okay, next we need to define points R and S. So we need to intersect AE with CD. AE with CD. Okay, so that's cool here in our diagram. That's easy. So this is point R. Next, we need to have point S intersect AE and DT. AE and DT. All right, so somewhere here maybe. All right, perfect. So that's our point S. Perfect. So now actually we just need to check that the order of these points, REAS, REAS. Perfect. So everything now is correct in this diagram. Of course, this is not our diagram that we will be solving the problem on. However, like this is just a quick diagram to know like how, like if our diagram, our big diagram should be similar to this one or we need to adjust it. Okay, so now that actually seems already cool. So probably we shouldn't make any change in this diagram at all. Like drawing such a pentagon is really cool here, because like everything intersects smoothly. Maybe just CT and AB were a bit like basically they are like somehow parallel here. They seem parallel. So maybe we just need to adjust that. Like maybe make CT bits more to this direction, so that they intersect more closely here, not like outside the paper. That means okay, perfect. So now we just need to show that P, S, Q, R are cyclic, or sorry, they lie on one circle. So P, R, Q, S. Basically, this quadrilateral should be cyclic. Okay, so what we'll be doing here now is we're going to erase the whole board now, and we'll draw this diagram. However, clearly we'll need to draw a very big diagram here on the board. All right. All right, so now we've just drawn a very big diagram, like it was the same as this small one we draw here. However, like this one is big, because ideally we want to do the angle chasing on the diagram, so we don't want to have a small diagram. All right, so let's take a look. Let's discuss the problem statement again. So we have a convex pentagon A, B, C, D, E, with the condition that BC equals DE. And then we have a point T, that satisfy three conditions. This angle is the same as this angle. This length, TB equals TD. Well, clearly, like the diagram is not that good, because clearly TB is smaller than TD. It's like shorter than TD. So like this is not like a really good diagram. In fact, like if you have a ruler with you, then you should like draw a better diagram than this one. All right, but guess what? Like I don't have a ruler here, so it's really difficult for me to draw like a really good diagram here on the board. All right, so we have that TB equals TD, and we also know that TE equals TC. All right, so that's like a bit better. TC is still a bit shorter than TE. However, like we can convince ourselves that TC equals TE. All right, next. After defining point T, we will define the four intersection points. So basically intersecting AE with CD at R, and AE with DT at S, and then we're intersecting AB with CD at P, and we're intersecting AB with CT at Q. And we just need to show that Q, S, P, and R, this is cyclic. We need to show that this is cyclic. All right. So first of all, let's take a look at our diagram and see like what can we conclude really fast. All right, so first of all, here we have a really cool diagram. This angle is the same as this angle. Guess what? Like here we have lots of equal lengths. This one is the same as this one, this one is the same as this one, this one is the same as this one. All right, so we already have a really nice thing, which is that this triangle CBC and triangle TDE, basically these are congruent. Why? Because from SSS, like all the sides are like all the side lengths are equal. Perfect. So now we even have three equal angles. So let's actually put these on the diagram. So basically like this angle here is the same as this angle here. All right, CB here. And this angle here is the same as this one here. And finally this one here is the same as this one here. All right, so now actually we have lots of equal angles, which is a good thing for doing angle chasing and like for noticing really cool ideas or cool properties here. All right, so now we have two congruent triangles, equal lengths and equal angles. All right, and we already don't forget that we have this angle is the same as this angle. All right, so now we need to focus what is our plan to show that this is a cyclic quadrilateral. So as you know, like to show that a quadrilateral is cyclic, we can do it in multiple ways, either with angles by showing like one of the properties of cyclic quadrilaterals, that, for example, the sum of two opposite angles is 180 degrees, or that two angles that are basically that they share the same segment or the same arc are the same. Like this is using angles. Or we can use power of a point maybe. Or like if we are intersecting the diagonals, then we can show that like the intersection of the diagonals, the power of this point, like to the two sides, basically it's the same. So let's take a look. Like, can we, for example, apply power of points here? Well, the intersection of diagonals is A. So basically, yes, we can. We just need to show that AS times AR equals AQ times AP. So that's a good idea. Maybe we will show that this is a cyclic quadrilateral using power of point. That's really awesome. Like usually it's a good idea when you have intersection of diagonals in your diagram, then it's really cool idea to just use power of point in order to show that your quadrilateral is cyclic. So maybe this is a good idea. Let's actually write it here. So maybe we just need to show that AS times AR is equal to AQ times AP. If we can show that, then we'll be done, clearly. All right. Okay. So now let's try to take another look here and see can we conclude something nice here, because as we mentioned, we have lots of angles here. Okay. So now we know lots of things about these angles are congruent, these two triangles are congruent. We know that this angle is the same as this angle. Can we combine these together to get something nice? Well, take a look here. This angle is the same as this one. This one is the same as this one. And this one is the same as this one. All right. So what about this angle and this angle? Take a look. This angle is the complementary angle of this one plus this one plus this one. The red one plus 1 green and 3 green. What about this one? Well, guess what? We also need have the red one here, the 3 green and 1 green. So guess what? These two angles are the same. That's really nice. Just like the triangle SDE and triangle CQB, we have this angle is the same as this angle. So that's really cool, cool thing here. So we know that this is basically the same as this angle. All right, so now we did use the fact that the angles are equal here to get this angle is the same as this angle. Now I want to ask you a question, what does this tell you exactly? When you see something like this angle is the same as this angle. This is really remind us of a really nice thing here. When we have a figure like this angle is the same as this angle. Clearly, they both share the same arc here. Well, we don't have the points defined. However, why not defining them? It's not a bad thing. If we the points are not defined, these two intersection points, we can define them, and guess what? We'll get a cyclic quadrilateral. So let's actually do that. That's really logical here and nice in order to use the fact that these two are the same. So we'll just define these 2 points here and here. Okay, so let me just call them maybe M and N. This one here and this one here. M and N. Okay, and now we just know that MN SQ is cyclic. Perfect. So what does that mean? MN SQ is cyclic. Well, remember, we want to show that AS times AR equals AQ times AP. But now, because we know that this one is cyclic, so we actually have that AS times AM equals AN times AQ. So something really similar to this. So let's actually write that down, what we know about this one here. So we know that AS is the same as this one, however, times AM equals AN times, AQ times AN. We know this. We want to show this. Well, if we compare the two relations by simply dividing them, because by dividing them we will get rid of AS and AQ will cancel as well. So we will get something really nice. Like what we need actually to show is simply AR over AM equals AP equals AN. That's what we really need to show. If we can show that, then we'll be done. So this seems simpler. So AR over AM equals AP over AN. Guess what? What does that mean? Like if you have a triangle ARP and you have 2 points on the two sides here, M and N, and you know that AR over AM equals AP over AN. Well, that actually is equivalent to saying that MN is parallel to PR. If MN is parallel to PR, like these two triangles are similar, AMN and ARP, and guess what? We will just get this ratio. So guess what? Now we just need to show that MN is parallel to this thing, to basically CD. So I just now need to draw the line MN. Alright, so let's do that. We just need to show that this one is parallel to CD. Okay, perfect. In fact, like you can actually reach this this claim to show that this is equivalent, like the parallelity is equivalent to solving the problem, to showing that this is cyclic in multiple ways. So power of point, using power of point, it happens just to be one of these ways. In fact, there is another way, like you can say that, like if you're familiar with the anti-parallel, like there's something called parallel, we already are familiar with, and something called anti-parallel. So like you can use the same idea here. We know that this thing QMNS is a cyclic quadrilateral. Furthermore, we want to show that QRPS is another cyclic quadrilateral. So that means that MN is an anti-parallel of QS and RP is an anti-parallel of QS. However, two anti-parallel lines for the same line happens to be just parallel lines. Alright, so if you're not familiar with anti-parallel lines, then just stick to this proof, using the power of point. It's really simple. We just need to show that AM over AR equals AN over AP, and this is just showing that MN is parallel to CD. Okay, so how can we show that this one is parallel to this one? Clearly now we just need to do angle tracing maybe. So let's take another look here at the diagram. MN is parallel to CD. What does that mean? Clearly, you can see that these two are intersections here. So this triangle and this triangle should be similar, right? We will have some angles. Basically, this angle should be the same as this one. This one should be the same as this one. That's what we basically need to do. So if we can show that these two are similar, we'll be done. So how do we show that they are both similar? Well, this angle is the same as this angle, clearly, because they are correspondents. They're sharing the same vertex. And to show that these two are similar triangles, we just need to show that Tm over Tn is equal to, Tm over Tn is the same as Tc over Td. So let's write that down. What we need to show is the following. Tm over Tn is equal to, okay, Tm will be opposite to this angle, which is the same as this one, so Tc over Td. We need to show that this is true. If we can show that this is true, then we're done. We will have shown that these two are similar, and that means that these two are parallel. So how can we show that this ratio holds, Tm over Tn? We don't know anything about Tm and Tn. However, we know what is Tc and what is Td. We can manipulate Tc into Te, replace Tc with Te, and Td with Tb. Like basically now we're making them closer to this, right? So actually we just need to show that Tm over Tn is the same as Tc now is Te, and Td is now Tb. So we just need to show that this is true. Alright, now clearly like Tm, like if we just like took Te here and Tn here, so we will have Tm over Te is the same as Tn over Tb. So basically, like we should have something really nice here, like this triangle MTE and NTB. Maybe they are similar, like maybe, because that suggests that the ratio of this side over this to this one is the same as this one to this one. So maybe these two are similar, and guess what? We already have that this angle is the same as this angle. Maybe, but is it true? We already have one angle. If we can find another angle, then we'll be done, because this will show that they're similar. Well, what about this one? Is this one the same as this one? What do you think? Let's take a look. Well, we know that this angle is the same as this angle. However, we know that the big angle is the same as this big angle, because these two are just like correspondent. We agreed on that, right? This angle is the same as this angle. And we know that this one is the same as this one. So guess what? That just means that, in fact, this angle is the same as this one. And we know that this one is the same as this one. So guess what? That means that these two triangles are similar. Meaning that Tm over Te, you can check that, it's the same as Tn over Tb. And you can replace Te over Tb with Tc over Td. And like that will show that these two are similar triangles. Guess what? That means that Mn is parallel to Cd. And simply that means that this is true. And thus, because this is true, then we get this is. And that just shows that our quadrilateral is cyclic. And so we're done basically. That is IMO 2022, problem 4. Alright, so as a summary, like this problem was not that difficult really. Like we have like a really complex diagram. However, don't fear that like complex diagrams, because if you like just know what you're doing basically and focused on the thing you want to show, like you will really like simplify the complicated stuff easily. So let's like discuss the problem again. So first of all, we started with the problem, we read the statement, we draw a small diagram in order like to do the adjustment for the big one. Don't immediately jump to drawing the big one. Start with the small one on the scratch paper and then go to like for the big one. Alright, so after we draw the big one, like of course like you should try to draw a more precise diagram than this one. However, like after we've drawn the big diagram now, we want to show that these 4 points are they basically lie on one circle. What is one way to show that basically this is cyclic? Well, because we have the intersection of the diagonals on the diagram already, which is A, like a power of point is really a good choice. So AS times AR equals AQ times AP. This is a good choice. Alright. Then we took a look like at our diagram here. So clearly these two are congruent triangles. This angle is the same as this one, this one, this one, this one, and this one. All of them are equal, and guess what? We know that this one is the same as this one. Alright, so like a quick look, by taking this one, and this angle, summing this one with this one and this one, like we will get that this angle is the same as this angle clearly. The angle Q and the angle S are equal. So that suggests that we draw like we put a point M and N here, and we'll simply get a free cyclic quadrilateral easily. And because we have the intersection of the diagonals on the diagram, still it's A, so we have this relation here. So that suggests that we take the ratio, like we defy the both relation over each other. And guess what? We just need to show that AR over AM equals AP over AN, which means that we just need to show that MN is parallel to CD. How do we show that this is parallel to this one? Clearly, we just need to show that this one is similar to this one. We already have one angle in common, so we just need to show that the sides have the same ratio. Tm over Tn equals Tc over Td. guess what? TC over TD, we can replace this one with this one, this one with this one. So now we just need to show that Tm over Te equals Tn over Tb. That suggests maybe because this angle is the same as this angle, that we show that these two are similar, meaning that we just need to have this angle the same as this one, which is clearly, like easily, this one is the same as this one because like we have the big one is the same as the big one and the green one is the same as the green one. Subtract them and you get this angle is the same as this angle, and basically that just shows that these two are similar, and thus like you can now go backwards to guess that AS times AR equals AQ times AP, and simply you will get by power of point, the converse of power of point, that this is a cyclic quadrilateral, and that's basically the IMO problem 4 of this year. Alright, so like my assessment for this problem, like I think it's easy actually, not that difficult, because like basically we just draw a good diagram, and like everything here was really classical. So like if you have solved some cyclic quadrilaterals problem before, you should immediately think of doing power of points here is a good choice, and clearly like deducing that these two angles are the same, and thus like putting a cyclic quadrilateral here is really like not difficult at all. Like reaching this point here is clearly easy, and like concluding that the parallelity here like should be true is easy, and like the rest is really not that difficult because like we're just drawing similar triangles and like we're just manipulating ratios and stuff like that. So like everything here is classical, so I really suggest that this problem is really easy, not that difficult at all. So in this here, like problem 1 and problem 4 were really reasonable. I believe like both of them were easy. Problem 1 probably was harder than this one. However, like that really depends on whether like you were strong with like you're more comfortable with combinatorics or with geometry. So like actually I'm more comfortable with geometry, so I really think like this one is easier than problem 1. But if you're like more comfortable with combinatorics, clearly like you will suggest that the like basically the opposite is true. That problem 1 is easier than problem 4. All right, we can say for sure that like this IMO so far like it's really cool. Problem 1 and problem 4 are really easy. Problem 2 was like between medium and easy, like you can say it's not that really difficult, like it's a bit easy, but problem 3 was really hard. So now we're left with problem 5 and problem 6. Will they be easy, hard, or medium? Like that's what we are going to like take a look in our next videos. Alright my friends, so I hope you enjoyed this problem. Tell me in the comments your opinion about this problem. Do you think that's easy, medium, or hard for you maybe? Okay, and please like, share, and subscribe to the channel, and see you guys in the next video.